Good morning. Thanks for joining us at LEDucation. Thanks for getting through that speedy badge line for those of you who made it through. Next time we're going to sell concessions along the line. That was an equipment delivery malfunction from yesterday. We apologize for that, as does the management company that works for us. So, a few housekeeping things before we get going. Online on leducation.org, somewhere on our website, you will find a speaker evaluation form. If you would please go at some point and fill one out for any evaluations that you attend today or tomorrow, that enables us to keep the bar pretty high as far as the quality of our presenters. So, I'm hoping that someone told you that if you need AIA credit, if you have an AIA number, not just a CEU, not an LU, an AIA number that you need credit for, there's a sign up. If you haven't done so and you need that, please do so at the main desk down by the main entry doors. If you need an LU or a CEU that's non-AIA number, you're already getting that via email, I believe, based on the fact that you got scanned coming into this room. So, Craig Berniker, founder of the Lighting Education Institute, an educational initiative focusing primarily on lighting education for professionals in the lighting and building industry. Professor in the Masters of Fine Arts in Lighting Design program at Parsons School of Design. From 1981 through 1999, directed the lighting education program within the Department of Architectural Engineering at Penn State University, and writes short bios. So without further ado, Mr. Craig Berniker. Doctor.
Thank you, Craig. Everyone hear me okay? Yes. Good morning. Controls are becoming such a big part of what we do in lighting design. And we're looking at it primarily from an energy perspective. But along with that, we need to really understand how the occupants of the space are going to respond to the control of light within that space. How many have heard of the square law dimming rule? A few. Okay. So we'll explain what the square law dimming rule is in a few moments. But basically, it's intended to try to represent what we perceive the light level to be in a space versus what's actually being delivered within the space. And it's not generally thought of as a linear relationship. So the obligatory AIA information is here as part of the presentation, and the learning objectives as well, but I would like to review those for a moment. So one of the things I hope to help you understand is that there is indeed a difference between measured light level and perceived light level when we're dimming or controlling a lighting system. And recognize that this square law relationship for dimming is actually a presumed relationship, and there really is not a research foundation for that square law relationship. I'll explain that as well. Thirdly, that recognizing or understand the importance of dimming to perceived level rather than measured level of light, and then recognizing this as an important part of the commissioning process, and that's not only making sure the controls work, but that they're delivering the light levels that we intend them to deliver at any one point in time. So to set the context for this is actually a project that was done as part of an elective course I taught last spring at Parsons School of Design with Parsons lighting design students who typically don't do research, but this elective was actually a research course where we taught them elements of how you do research, hopefully with an applied focus. And the experiment that we did that I'm going to show you today was actually the class experiment. So we had 9 students as well as myself who both designed and executed the experiment as well as doing the analysis. So I'm going to talk a little bit about the background that underlies the square law dimming curve and why that's a presumed relationship. Walk you through the methodology of the actual experiment, the experimental setup, and what we did in terms of gathering data from the subjects. I'll show you the results then as well, and then talk about some conclusions. And then hopefully you'll have some questions that I can answer for you at the end. But I'm going to start by doing something that's very dangerous in a live presentation. And that's going to be that I turn the lights out first, which means that you might fall asleep while we have the lights out. But more importantly, yes, can we turn them off? There's always the risk of this not turning out the way it's intended to be because it's a very uncontrolled environment. So I've got a standard reflector type lamp that's projecting light on the wall. And I have a light meter so we can measure the light, and right now I have it at 100% of the output. So I'm going to measure that, and I'm going to try to get as close as possible to the center of the beam. You'll have to help me adjust when I measure again to make sure I'm in about the same location. But we're in the neighborhood of about 35 foot candles being delivered by that light source right now. So now I want you to tell me when you perceive the light level on the wall to be about half of what it is right now, about 50% of what it is now, as I dim it down. Can you just call it out? About there? So now we're measuring about 10-foot candles, as opposed to the 35-foot candles that we started with. So what would we expect the lighting level to be if indeed our perception lined up with the measured light level? Somewhere in the neighborhood of 18-foot candles or so. So we actually are delivering less light than that, but we are perceiving it to be half of the light level that we started with. And I can breathe a sigh of relief because that worked pretty well, so I'm happy about that. So let me give you a bit of background then on the square law dimming. So this is a curve that has appeared in the IES handbook for quite a number of years, several editions. This is actually from the 9th edition of the handbook, and it's showing the square law dimming curve. And the square law dimming curve basically relates, again, the relative light measured. So on the vertical axis, we have the relative light measured. Can you read well enough in the back, or is it helpful if I point to things up there? Point? Okay. So this axis says relative light measured, and this says relative light perceived. And there are a couple of dashed lines drawn on the curve. Basically, this is the curve that relates the two. This is the square law curve. And if we look at a couple of illustrations, and I do have it highlighted here, so that might be helpful as well. So if we look at basically what you just did with me, you said that you were perceiving 50% of the light, but I was measuring less than that. And as the square law curve shows here, 50% perceived light would be equal to 25% delivered light. So you'd actually be dimming down 75% for us to perceive that to be 50% of the lighting level. So it's basically a relationship of a power of 2 when we talk about the relationship between perceived light and delivered light. So that's the perceived light, again, on the horizontal axis and delivered light on the vertical axis. Now, in that 9th edition of the handbook, this was referred to for the first time as a presumed relationship. As I said in the beginning, there is no solid research basis for this relationship, so it's one that's been assumed for many years. And if I look back in history a little bit, there's some folks who have related it to the way we specify colors in the Munsell system, where the value of the color relates to the reflectance by a power of 2. And that's really the only evidence that I could find along the way that would give us some idea of where the square law relationship has come from. And that obviously is referring to surface colors as opposed to light. Finally, in the 10th edition of the handbook, the most recent version of the handbook, you'll see a different relationship. No longer are they talking about a square law relationship, but in one of the fundamental chapters of the handbook, they are showing us a relationship simply between luminance and relative brightness, which is essentially the same sort of thing, right? How much light's being delivered or how much light's coming off a surface versus what we perceive the brightness of that surface to be. So here's luminance now on the horizontal axis measured, so they sort of flip this, and there's relative brightness on the vertical axis. And you'll note that it says a luminance brightness power relationship based upon an exponent of 1/3. So essentially, instead of a power of 2, it's a power of 3 in terms of the relationship as shown here. Now, this has some basis in research over the years. If you look into the psychological literature in particular, you'll find that there's a whole area called psychophysics, which is simply looking at how we as humans respond to physical stimuli, psychologically respond, sensation and perception relative to physical stimuli. And there are a number of researchers who've been very famous in the psychological literature, Weber and Fechner and a couple of others, but probably the most important one from our perspective would be Stevens. And Stevens has looked at a number of physical stimuli and how they relate to our perception of those stimuli. So you'll see on this particular graph, electric shock is one of those. I'm not sure we'd get away with doing that today, but he did in the 1970s. Apparent length is another, and that seems to be pretty much a linear relationship. Let me point again here. So there's electric shock, there's apparent length. And then the third one he looked at was indeed brightness. And this axis is the stimulus magnitude, the measured level, so to speak, and this is the psychological magnitude, the perceived level, so to speak. And you can see that, again, apparent length is a linear relationship, but the others are power relationships of one form or another. And if you dig a little further into this, you'll see that Stevens has done even more than what's shown on that graph. You'll see a whole slew of things that are shown here, thermal pain being one of them, for example. But right here on the upper left-hand side, you'll see, and I've boxed them in, that he's actually done a series of brightness perception experiments and measured exponents of 0.33. That's where the IES graph came from, 0.5, 0.5, and then 1.0, shown successively in the table here. Also note that the 0.33 relationship is basically looking at a 5-degree target in the dark. And I'll show you an illustration in just a moment. That's basically a very small spot of light that is being viewed in the dark. Nothing quite related to what we see in an actual room or in real life. Next was a point source, then a brief flash, and then a point source briefly flashed. In any case, it's this 5-degree target that was the basis for the power law of 1/3. So again, this is simply a very small spot that's imaged in the fovea of our vision, as opposed to something that would be in the full field of our vision. And you can see that illustration right here. There is our 5-degree central vision, which is basically something imaged in the fovea of the eye. Yet we're seeing a much wider field. So this gave us pause to say, what happens to this relationship if indeed we're looking at something larger like a room surface in an actual room relative to the perception of light that's being delivered or dimmed along the way? So that's a little bit of the background behind why we did this. So let's move to the methodology a bit. So we did this at Parsons in the School of Constructed Environments in our light lab there. We provided a uniform field of luminance controlled by a dimming control system. We used 2 LED theatrical luminaires, as you'll see in some illustrations in a moment, to project light onto the surface. We debated for a long time whether we would try to make the surface itself luminous and whether it should be an overhead surface or a surface in front of you. And for this study, we ultimately decided that it should be the surface in front of you, a vertical surface, because that tends to fill more of your field of view than an overhead or an underneath or even the side walls in the room as well. And the theatrical luminaires gave us enough punch to have some reasonable changes in luminances on that wall. They were mounted approximately 25 feet from a diffuse colored surface, actually not much different than the upper portion of the walls in this particular room, about a 50% reflectance. This is actually part of some equipment we have in the lab that's used for daylighting studies. It's actually a diffuse sky simulator. So we have a couple of walls that can pull out and create a small room with a luminous ceiling overhead, with mirrored surfaces to make it look like you can see all the way to the horizon. But we modified this a little bit so that we could use it for this particular study. So we actually closed the walls again and to have this neutral surface, as you'll see in just a moment. So here's an illustration of the plan. You can see the wall that the light was projected on is right here. This is basically the diffuse sky simulator. The subject was seated just about 8 feet away from that wall. We had black curtains hanging on either side to minimize the influence of the side walls, so we're simply focusing on the front wall. And you can see where the students sat as experimenters to be able to adjust the dimming levels that were presented to the subjects, as well as to record their responses. Here's a sectional view of that as well. Now you can see the theatrical lighting fixtures. They probably should be angled up a little bit more in terms of the surface that they were covering here. Here is the subject position once again, and then the experimenter positions. We had the experimenters behind, so they weren't in the field of view of the subject. And the theatrical lights were positioned such that the subject himself or herself was not casting a shadow on that front wall. So we were maintaining that uniform luminance on the front wall. Just an illustration of the theatrical luminaires and the control equipment that we used for this particular study. And I'm not supposed to tell you trade names, so we've left those off the slide. But you can find those if you really want to. Anyway, there is an illustration of the control equipment where the experimenters sat, and a couple of the experimenters actually running through the experiment. You can see the subjects seated over here as well. This is a photo of the front wall on the left, basically showing you the reflectance of that wall, but also showing you one of the students who was actually doing chromaticity measurements. So one of the variables that we wanted to control in this particular study was the color of the light that was on the wall. So that wasn't influencing the perception of light level. Unlike what I had up here, which is basically a light source that dims to warm, so color might have influenced your perception to some degree. You can also see then on the right the two theatrical lights and how they were positioned to illuminate that front wall. You can also see a luminance meter sitting right here. We actually had two luminance meters positioned so we could measure the luminance of the front wall to make sure that it was constant throughout, so that it wasn't changing to variations in voltage or other things that might influence the levels of light that were being delivered to the subjects. 28 subjects, which were drawn from the student population at the new school and neighboring institutions. 5 different institutions, actually. Our students reached out to quite a number of friends and others in the community. All naive subjects. And what I mean by that is they didn't know anything about lighting. We didn't use any of our lighting students in this particular experiment. 18 female and 10 male. As you can see, the average age was about 26, ranging from about 18 to 32. 10 subjects were American, and the remainder from various other nationalities. So we had that range as well. And although we didn't test their vision, we did ask them very specifically if they had 20/20 vision or corrected 20/20 vision, and asked them to wear their glasses or contacts or whatever, so that they were as close to 20/20 vision as possible. That's a typical thing you do in a study like this. And if it was more of a concern, we probably would have tested their vision as well, but some variations from 20/20 vision wouldn't influence the results all that much. So again, they were seated at that fixed location. Actually, it was closer to 8 feet from the wall than 10 feet. We actually asked them to focus at a spot on the wall, right in the center of the wall, when they were making their judgments, so their gaze wasn't wandering too much. So If that would occur, they might be taking into more of account the sidewall, for example, with the black curtain or something like that. So we're asking them to try to hold their gaze as much as possible on the front wall. Again, if we were really concerned about that, we would probably fix their head. You can have a chin rest, for example, in a study like this where you would fix their gaze as much as possible. But we thought this was adequate for this particular purpose. Subjects were tested individually, so one by one, and they were initially exposed to the full intensity of light, just like we illustrated up here, and then they were asked to judge or rate the subsequent levels as a percentage of that initial level, again, as I asked you to do as well. So they were presented these in sequence, always the 100% output, and then randomly selected different levels or percentages of light level being delivered to them that they would have to then judge. There were 50 different lighting levels. We divided those into two sets of randomized presentations, which meant, as we learned, that by the end of the testing, the subjects were pretty fatigued. And we looked at that, but interestingly, it didn't affect our results much at all. And again, they were exposed to that base level 100% as a base level for comparison for each presentation. This is just a bar chart basically showing you the number of different settings in a particular range. So from 0 to 9%, for example, here, we had about 12 settings. 10 to 19, we had somewhere in the neighborhood of 13 settings, and then so forth. Again, these were randomized to some degree, but also recognizing that when we look at a power law curve like we were looking at, the lower settings become more important. And you'll see that in some of the graphs that I'll show you in just a minute. As I mentioned, we took luminance measurements for each dimming setting from two different locations, two different luminance meters, so we could validate the measurements. They were slightly different, so we were actually looked ultimately at the data from both of them. And fortunately, that turned out to be very similar. And we also did some high dynamic range imaging of luminances. I'm not sure if you're familiar with those techniques, but you can use a digital camera and some software to actually create a map of the luminances of a particular scene. And we did that actually with a digital camera and also with some apps that have been produced recently to do some of that digital luminance mapping for you, which we've actually tested in another study, but that's another time. Again, we took our luminance meter readings at the same location that we're asking the subjects to gaze at, so we're basically measuring at that particular position. And as I said, we took color temperature measurements using a chromaticity meter to make sure that we weren't varying color from scene to scene or adjustment to adjustment. Here is just a photo of the wall itself and then a pseudo color on the right showing the luminance map. Try to give you some sense for the degree of uniformity, and you can see that we're within a 2-to-1 ratio from the highest luminance on the wall to the lowest luminance in the corner. I'm not sure we could do a whole lot better than that in terms of uniformity, so we consider that to be pretty uniform. Then the results. So first I'm showing you the average perceived levels of the subjects along with the error bars that represent how much variability there was amongst the subjects. So there's the average or mean, and then there's the variance that's indicated by the little lines at the top and bottom here. So that's the mean, and then the line there and there represent how variable they were. The purpose of doing this was to see, were all the subjects adjusting to basically the same level, or were some adjusting to really low levels, some adjusting to really high levels, and the average isn't quite as meaningful then. But when we looked at the data here across the different 50 dimming settings, the variability is quite narrow. So there wasn't that much difference between how the subjects rated the different levels of light that they were being shown. This graph shows the mean or average perceived lighting level versus the actual dimming setting. So if you look at this axis, this is the dimming setting in percentage, and this is the perceived adjustment in percentage. And you can see that there's a fairly close linear relationship between the dimming setting and the perceived adjustment of the setting. So in other words, if we adjusted it to 50%, the subjects were basically saying that was 50% of the light. Now, at first glance, you say, well, that means it's a linear relationship. It's not a power relationship at all. I hope that makes sense. And notice, by the way, the correlation is a 0.95. But if you take a step back and you look at the manufacturer's dimming settings, as many manufacturers do, they were using the square law dimming to set up their settings. So essentially, this is reasonably close to a square law dimming relationship. And the next graph shows that fairly clearly. This is now the luminance measurements we were taking versus the dimming setting. And if you look at the curve there, it's incredibly high correlation, R-squared value of 0.9976, almost a perfect relationship there. That's essentially a square law curve. So basically, the dimming settings were following that square law relationship. Okay, I hope that makes sense. Finally then, now we're looking at the perceived level versus luminance. So again, the distinction here is one of the relationships we looked at was the percentage of light that the dimming system said it was delivering versus the perceived level. Now we're looking at the actual luminance that we measured versus the perceived level. And when you start to look at this is a curve fit to the data. This also has a high R-squared value of about 0.95. But what's important now is to look at the exponent up here. And I know at this distance, you guys probably can't see that at all in the back. But it's a 0.428. That's not a square law relationship. That's a different power law relationship than a square law relationship. This, by the way, is measured luminance number 2. This is measured luminance number 1. So the two different luminance meters now. And now this is plotted with the mean perceived level against the measured luminance from meter number 1. And again, you see a pretty tight curve fit to that, pretty high R-squared value, almost 0.95. And the exponent here, again, is a point, and I can't see it there either, so I'll have to read it up here, a 0.4292. So if you round those, for both of these, luminance meter measurements relative to the perceived level of light, we're looking at a power law relationship with an exponent of about a 0.43, not a square law relationship. So what does all that mean? Well, first of all, there's clearly not a linear relationship. There's a non-linear relationship between luminance and the perceived level of light, as it's judged as a percentage of the initial level that's being delivered. For both sets of luminance measurements, the relationship between luminance and perceived level of light followed that power law of about 0.43. So our measurements and the perceived level matched up very closely with a power law with that particular exponent. And what that suggests then is that neither the square law dimming relationship that's been presumed for many years, nor the brightness power relationship that Stevens proposed using the 5-degree visual field and with an exponent of 0.33 really explain what our subjects were seeing in a more full field environment. So neither hold for the data that as we basically collected it in this particular experiment. Now, this is not inconsistent with some of the other studies that have been undertaken to determine this relationship, although none have done exactly what we did. So some were dealing with an object background luminance brightness relationship where you're trying to estimate the luminance ratio between an object and its background. That was Bodman and Latoyson in 1994. are more complex visual fields where you've got lots of things going on in the environment, which we do in real environments. And that would be a next step that we would want to look at. That was Marsden in 1970, where he's looking at multiple surfaces in a field of view and had a power law between luminance and brightness perception. And actually, in both of those sets of experiments, there was it was somewhere between a 0.35 and a 0.6, which to some degree is consistent with our results. We fall within that range as well. So what does all this mean? Well, I think we have a better sense for how we might set up our dimming controls. And one of the questions to ask ourselves, a very important question, is how much does it matter? If a manufacturer follows a square law dimming curve, is it all that much different than if it follows a power law with a 0.43 value? And I think that is a question that remains to be answered, that we need to do some subjective studies with folks and try to find out how important that relationship might be. Some other things that we think are important is to expand the range of luminances. We were probably not above 80 candelas per square meter with the luminance on that particular wall. And we obviously have larger, higher luminances in the field of view that might be influencing our perception of brightness within a space relative to dimming control systems. The position of the dim surface. Again, we decided on this vertical surface in front of us, but what if it is the surface overhead that really is the dominant surface that's being dimmed, and the walls are sort of secondary in some fashion, so overhead or in front of us. The uniformity of light, what about non-uniform patterns of light on a surface, on a vertical surface, for example? So scallops of light around the room. And I just noticed that we never turned the lights back on, and I apologize for that. We sort of intended to do that. And I apologize to the videographer because he wanted the lights on so he could video a bit better. Surface luminances versus the luminance of the source. So basically light reflected off the surface versus the luminance of these luminaires. And if we're dimming the luminaires, is that the dominant element that we respond to as opposed to the surfaces in the room? Color of light, warm versus cool, will that influence our perception of the change in dimming level and luminances of surfaces? Well, the colors of surfaces, we used a very neutral surface, so if you have more saturated colors in an environment, would that influence your perception as well? And although we didn't find any in our study, and you saw that there were a fairly wide range of gender and cultural differences, we did not find any differences, but exploring that more, I think it would be appropriate, culture, age, and our gender differences in brightness perception. So that's the study that we've done. It's really intended to be somewhat of a pilot study. It was really trying to address that question, is the square law relationship something that is valid to some degree or not? We think we have a better relationship that could be used by dimming manufacturers, but there still would be a fair amount of work that would need to be done, I think, before we could conclude that without question at all. Again, this was in a study done with 9 graduate students at Parsons, and we are publishing a paper on this in the IES journal, LEDucation, in the near future. So if you want to recognize the students that were involved in that, you may want to find a copy of that when it's ultimately published. And I just wanted to open the floor for questions then. So, yes?
I understand the reason for the study and exploring how we perceive light as opposed to how it might measure the meter. I don't know that I understand how that's relevant for dimming system manufacturers. I understand that historically dimming system manufacturers would program their modules with the square law because they were dimming incandescent sources where regulating the voltage was going to dim the light in a known way. But with other sources that people are using now, if you don't know what the source is, and you don't know how the driver is going to respond, the dimming manufacturer doesn't necessarily have any idea how they regulate the power is going to affect the lumen output of the source.
Okay, so
So, I understand the study, but not how it necessarily pertains to control systems.
So, first off, if we go back to our example of the square law dimming that was in the graph on the screen, so when the perceived level was 50%, we were actually dimming down the delivered level by 75%. Now, I think your question is, how does the actual level of light delivered relate to how much power is being consumed?
Right, because that's what the dimming system's actually doing.
Right, and we would need to explore that. The assumption is that you would be saving far more energy by delivering a quarter of the light rather than 50% of the light, because you're relying on the perceived level rather than the actual delivered level. I hope I said that clearly. But I think that's an important relationship to look at. Yeah.
What you might be including as well is you gotta remember when someone's designing something in, and if you're using 50 watts in reference to driving a system, now you're dimming it down to 50%. The perception is you're no longer doing 50 watts, you're doing 25 watts, and that's not necessarily true in reference to the power, because you can still be higher. It's gonna be based on whatever dimming protocol they put in. So it's not a linear. And that's what we run into too in reference to manufacturing, in reference to one was specifying, because you're trying to drive down wattage, obviously, to meet a performance.
Yeah, that's what we've seen as well, that a variety of manufacturers are using different protocols to basically identify the percentage of light that you're dimming to. So this hand control, when you said it was 50%, I was halfway with the control. So the control is actually designed following that square law dimming relationship. So the movement of the control is intended to try to represent that. And as we actually get to lower levels of light, the adjustment becomes a bit finer. So when we get to that really knee in the curve of the power law relationship, if you want to dim down to 10%, you need enough adjustment in the control to enable you to do that, or you're going to jump right down to zero or turn off. So you've got to have enough play there. So a lot of manufacturers have designed their physical controls to have that kind of a relationship between the physical adjustment of the control and the perceived level of light. But some are using square law, some are using other relationships as well. It would be nice to have a consistency amongst those relationships.
What was your transition rate from setting to setting during the study, and does that impact?
Yeah, there was a 30-second adaptation time between the settings. So we went to 100%, basically went to dark for 30%, not completely dark, but then presented the second setting to them. Question in the back? Yeah, yeah, sorry.
Suppose that if I want to change the CCT of the room, if I keep the rooms, like photometric or lux rating is the same, just changing the CCT from 2,000 or 3,000 to 5,000, just keep the lux rating the same. To the human's feeling, is it like, still feeling the same light level, or it would change?
Well, we're trying to hold that constant in this particular study. But in general, you're going to perceive higher color temperatures, and I hesitate to say that because it's more spectrum-based than color temperature-based. But you'll perceive blues basically to be brighter than greens or reds. That's a function of how the visual system operates. But we didn't test that at all. We were holding color temperature constant here in this particular study. But that would be something that would be worth exploring as well.
Is there an intent to further study with different people?
That would be, we haven't planned out a specific agenda yet, but as I said in that last bullet point, age would be one of the things that we'd want to look at. Recognizing that those of us who are over 50 can only process as much light sorry, half as much light as when we were 20. So that would be worth evaluating. And we lose our ability to see blues, basically.
As someone that is in the industry, and people are using dim lit light 50%, if we were to actually change that curve, how difficult do you think it would actually be for designers to adapt their pre-programming and their mentality for the new setting?
I don't think it would be difficult at all because I think most designers aren't actually paying attention to that. I don't think that they actually know that manufacturers are adjusting their controls relative to perceived versus delivered levels. I may be wrong about that, but that's my sense. I see a head shaking no. Is that?
They typically design with the eye where it's not.
So when you're doing the experiment, so you have exposure for how long between the 30-second adaptation?
We presented the initial luminance for 30 seconds, then 30 seconds adaptation, and then they had until they told us the percentage. So they're reporting that to the experimenters. So
So during the sequence of the experiment, they start always at 100%, and then the experimenter takes it.
no, it's all randomized.
Yeah, right, that's what I'm trying to understand.
Yeah.
But ultimately, they're referencing to the 100%, and since we don't have visual memory, so how are you doing the randomization?
So they're seeing 100%, and they're given another pre-adjusted level, and that could be completely randomized. Okay? And then they're reporting their perceived level, right? And then another 30-second darkness period, right, adaptation period. They're seeing the 100% again. Right, and then they see again. Okay, so they're always judging it. It's a paired comparison, basically.
So you always have to have that reference?
Yeah.
in the
Yes.
sequence.
We felt that was important. Other questions?
I'd like to ask a very general question. There are some manufacturers of driver companies provide dimming curves for common drivers. They provide like algorithmic.
That's-
and, square dimming. Are those two any differences between them?
So the last part, are they?
They provide like the logarithmic dimming curve and the square dimming curve. Square root dimming curve.
We haven't done a thorough study of which manufacturers are using which curves. It's more anecdotal. I was one of the next generation luminaires judges when we were doing or introducing controls, and one of the problems with judging the different products was the different control protocols that were being used to dim those products. So it's more anecdotal that I can tell you that, but it would really be worth, I think, looking at which manufacturers are using which protocols to get a handle on that.
The answer on that is actually yes, and a couple of them actually allow you to change the curve that you're using reference dimming. So we've used ours when we use advanced, you can actually change it, the logarithmic, and then there's another one, there's two different ones you can select, and then,
Good.
again, it didn't equate the wattage. That's what our problem was, we're trying to equate the wattage reference dimming, where you got the perceived, where you got the curve, it's a very,
Right.
pick your poison type of situation.
So we thought this was a first step, and then looking at things along those lines would be subsequent steps that we'd want to take. Just to give you a little more context, Parsons is indeed a design school. They have not had a research culture in the past, but we're really trying to develop an applied research culture. So this is one of the first steps in attempting to do that.
Thought process with respect to the question.
I can't quite hear, I'm sorry.
Where the light source is being located, do you feel like that would have a difference effect versus yours?
I would think where the luminaire is positioned in the field of view could potentially have a significant effect, where you're really responding to the change in luminance of the luminaire as opposed to the surfaces around. Yeah. If it's back there, probably not. If it's right there in your field of view, probably so. Yes.
Just a quick question, were the fixtures changed tungsten or daylight?
They were 4,200 Kelvin. Yeah, so in between, right? Neutral color to start off with. Okay, well, thank you. I appreciate it.